all the nodes right in the network. So maybe in a communication network, we want to connect all the devices by cables, and in the networking network, we want to connect all the cities by roads. And one phenomenon is that they are not perfectly reliable. So these edges of these links may be liable to failures. We want to study how robust is a network to stay connected under edge failures. So this is a very natural goal of evaluating a network. So to study this question, we can consider two settings of edge failures. The first is worst case edge failure. So assuming you have a few edges that might fail, but this can be chosen by a diverse group. So say k edges will fail, and whether the network will stay connected after removing any k edges in the worst case. So this will give us a connectivity or min-cutting problem. Right, so you are just trying to find the worst way to connect to disconnect the graph, which is the minimum cut. And you can define this problem for different notations of connectivity. Right? So this is a very fundamental problem. But another very fundamental setting is we consider the edge failure in random manner. So this is also natural when we don't have much information about edge failure. So we can assume, well, each edge will fail independently with some probability, and say we have some statistics for this probability. So this will give rise to our network unreliability or reliability problems. So now we can rephrase the question as how likely does the network stay connected under random link pairs? And this is a key question in the field of network reliability with network stability. So more formally, we can denote, well, given the undirected graph G, we consider, say, undirected graph. And we consider a random graph G of T formed by removing each edge in the graph with independently with probability, for given uniform probability. So here, we graph that, well, it's in general, we may consider different failure probabilities for each edge. But we can also, like for simplicity, we consider uniform failure probability. This is not without loss of generality, because you may simulate non-uniform failure probability by introducing multiple parallel edges. So if you have two parallel edges with failure probability, then this is equivalent to one edge with failure probability p squared. So in general, this is not too loss of generality. So let's just consider this uniform model for simplicity. Now we can define this reliability and unreliability to be just the probabilities that such a random graph is connected or disconnected. Okay. So the key problem, of course, is to compute these two values. And of course, these two problems are equivalent because it's just two probabilities that sum to 1. But unfortunately, this problem is in the first list of Sharpie half problems given by Valiant in his in his classical paper introducing the Sharpie class. And recall that Sharpie is the complexity class of counting number of feasible solutions. So it's harder than NP and unlikely to compute the exact value in polynomial time. So what we want is some good approximate algorithms. Okay. Now, for the approximation version of these problems, they are no longer equivalent because their hard cases are opposite. So we are trying to get a multiplicative approximation of a probability from 0 to 1. So if it's very close to 1, we can simply auto 1. So it's very close to 0, we have to auto a tiny measure. Yeah, and one of the good form of approximation algorithm is such a fully polynomial time randomized approximation scheme, or FPTAS, which simply means we will count the one perception approximation of this value in polynomial time and polynomial in n and 1 by epsilon. So we get a inverse polynomial small letter epsilon and succeed to high probability. Unfortunately, such a strong version of approximation algorithm is known for both problems. And for unreliability is given by Karger in 95. But for reliability, we know it's much later, by Cohen Jeremy, 2019. So this we know much less for the reliability problem. And this talk I will focus on the unreliability problem. is a probability. Just feel free to stop me for any question. Okay, so let's look at the major results for this network unreliability problem. We have the first FPTAS by Karger, and this algorithm and the one following algorithm by Karger is three methods. They use this Monte Carlo and DF counting technique. So this is like first generation. And then in the second generation, we have a series of works by Karger from 2016 to 2020. And he extensively explored this random construction algorithm and improved runtime to near quadratic. And after that, we improved in our previous work, we improved runtime to 1.5 by combining the random construction algorithm with a new algorithm idea called inference sampling on tree packing. And finally, in this work, we follow the same framework, but we introduce a new ingredient called ideal tree packing to improve this analysis of these two algorithms, random construction and inference sampling. And finally, improve runtime performance. So this is a slide overview. But in this talk, I want to introduce these two algorithms, that is random construction and inference sampling on tree packing. And after that, I will introduce ideal tree packing and briefly discuss how it can help these two algorithms. Okay, so let's start with the simplest algorithm, that is Monte Carlo. So you just draw the sample according to the definition, right? But in more detail, we can say, well, we toss a coin for each edge. The coin has head probability P. They're independent. So each edge, we delete the edge if this coin's head, right? So it happens with probability P. And if you draw the sample, of course, this sample graph A will follow our target distribution G of P. So we just remove each edge with probability P as we desire. And then we can define the estimator to be the indicator that the sample graph A is disconnected. And of course, the expectation of X is just the unreliability, just a probability to disconnect. And since X is just a Bernoulli random variable, its variance is just U times 1 minus U. So for such we can consider relative variance. That is just if you scale the expectation to 1, the variance will become something like 1 over U. And now if we have a random variable that has expectation 1 and variance like bounded by some polynomial, you can take polynomial samples, take the average, and get a constant approximation with good probability. So this is the algorithm. Like it will be efficient if we only care about polynomial time. We can use this algorithm when your unreliability is at least some inverse polynomial. Because in this case, your estimator will have a relative variance bounded by some polynomial. And then you can repeat this algorithm by taking average of polynomial main samples to get a constant approximation. Okay. So this is the simplest algorithm, but it shows some idea of how we can handle such a problem of estimating a probability. That is, we want some unbiased estimator that have bounded relative variance. And we try to reduce variance by taking average and finally get a constant approximation. So this is our goal. Okay. And the bad case is really when your unreliability is very small, so you cannot directly do this Monte Carlo sampling. The Monte Carlo sampling will be bad because intuitively one reason is that you are revealing too much randomness using this coin. So one idea to improve it is we can use 2 coins instead of 1. And say for each edge we toss 2 coins with head probability Q and P over Q for some Q greater than P. And then we remove the edge if both of the coins are head. Right? So this still happens with probability P, which is Q times P over Q. So if we just draw a graph according to this procedure, we still get our sample graph A following the same distribution. But now the trick is we only reveal the information of the first coins. So that is when the first coin is tail, this edge cannot be removed in the final graph. So this edge must be connected in the final graph. And since we only care about connectivity we can safely contract this edge without changing the connectivity of the resulting graph. So let's say H could be the random graph formed by contracting the edges whose first points are tail. So this will not change the connectivity. And then we still have to review the second point. And the second point is that we will remove the edge if the second point is head. So this happens with probability P over Q. So the final example we draw is just A prime is from H, but we remove every edge with probability P over Q. So this is exactly the definition of H of P over Q. Okay. So this argument is just some coupling that says, well, if I draw a sample A prime by first draw this random contraction H, and then we remove each edge with probability P over Q, this should have the same connectivity as A. And now since the probability that A fail is UGP, and the probability A prime fail for fixed H is UH of P over Q by definition. And then we take the expectation of H to handle the randomness of H. Then we know that, well, these two probabilities must match. Right? So we get unbiased estimator UH of P over Q. That is, for a random graph H, we can compute this value. Assume, say, if we guarantee the H is very small, we can compute this value. Then we can use this value as an estimator of our final unreliability. Okay, so we have this algorithm, and this is just the random contraction. Okay, and one more step further, we can observe that this UH of P over Q is a subproblem of the same format as the original problem. So we can, of course, we can recursively apply the same step on H. So if you keep doing this, maybe you finally get some very small graph after some contraction, so you can solve it equal force, and you can scale back to get the original estimator. But the problem is if you repeat this step many times, each time your randomness of H will create some variance, and these variances will accumulate, you might get a very bad estimator. So one way to handle this is instead of one sample H, we can draw two independent samples of H in each step of regression. And then we recursively estimate UH1 and UH2. And we take the average to reduce the variance of this step. So if you do this in every random recursive call, you should be able to bound the overall variance of the overall estimation. So some calculation here is that we can choose this permanent Q. So we somehow choose this Q to make this relative variance of one step to be 2. So Q might be very close to P. And then since we run these two samples or more samples, we can reduce the variance to 1. But this creates multiple subproblems in each recursion layer. And if we have a good recursion tree, say the depth is bounded, then the overall relative variance should still be constant. So we can get a constant approximation in just constant samples. And but each sample will involve really a whole recursion tree. So this will be some polynomial time. Okay, but for this idea to work, you really need the subproblem size cannot be too large. But if you have two subproblems with both of them have like size n of say same as the original problem, then your total size will explode. So ideally, we want when we have two subproblems, each subproblem size will be half. And can this be achieved? Well, in some cases, we can. So let's just focus on one main cut. If you only consider one main cut, it's there are lambda cut edges, and each edge will not be contracted with probability Q. So this means you will not contract the main cut with probability Q raised to lambda. So this is some like 1 over alpha. And then as we argued for a Bernoulli random variable with like 1 over alpha, its relative variance will be something like alpha. Okay. And but this is only for one main cut, but in general, general, intuitively, if you have more min cuts, they should somehow cancel out the randomness in there. So maybe this variance will be suppressed. And actually, but this is very vague. But actually, something like this can be shown that for our x meter of UH of your cube, its relative variance can actually be bounded by something like alpha. Here, I mean, there might be some tiny constant that we can ignore in the analysis. Okay. So this means we need alpha branches of recursion to cancel out this relative variance. And then, how much size we can reduce in this compression? Well, if you consider simply that you have a path of n min cuts, so they will be independent, and each will not be contracted with probability 1 over alpha. So after this compression, you will, in this situation, have n over alpha cuts. Right? So your path of length n will shrink to a path of n over alpha. So this is actually good because we have a recursion that each step you have alpha subproblems, but each subproblem has size n over alpha. And this will give you a linear recursion. So you have log n layers, and each layer, the total size is this. So this is actually good. But in general, there will be some bad case. So there might be more min cuts, and the worst case is you have a cycle of half of n min cut, cycle of n square min cuts, because every pair in the cycle will be a min cut. So in this case, if you repeat this argument, you will find that, well, each cycle edge will now not be contracted with probably q to half of lambda. So this is 1 over root alpha, and your cycle will be contracted into a cycle of size n over root alpha. So if you do this calculation, this will become a quadratic recursion. You have alpha branches, but each branch only shrinks by root alpha. So this is this is the Karger's optimum, but it's bad for our goal because we want a linear algorithm. And some hope here is that, well, since you have so many min cuts, their variance should be small, as we argued for the big intuition that somehow they can cancel out. This is true in the example of a cycle, but this is still there will be some really bad case. That is, you have a cycle of near min cuts, so they will stop you from any contraction speed faster than root alpha. But there is also a min cut, and this min cut will dominate your unreliability. And this cycle of near min cuts, although there are many near min cuts, they are still insignificant compared to the real min cut. And this will make the variance also close to 1 min cut. So your 2 bound is really tight in this case, and the quadratic recursion is the best you can have. But for this bad case to happen, you must have very small p. Because now I'm assuming you have n squared near min cuts, but their total failure probability is still much less compared to 1 min cut. Okay, so they maybe n squared times p to 1.1 lambda is less than p to lambda, something like that. So I'm just saying, well, this will force your unreliability to be small. So our plan is actually, given this proposition, our plan is to improve the random compression analysis when your bounds are not so tight, when your p is not too small. So we call this unreliable case when your p is large, basically. And then when p is small, we need a different algorithm to handle the case. Yeah, I will come back later. How can we improve the bounds, even given this stronger assumption? But now let's switch to the reliable case and see what can we do in a different algorithm. Okay. So now we are in the reliable case where the p is small, so it's unlikely to fail. And let's consider the extreme case, that is p approaches 0 in the limit. So in this case, I'm saying I claim that you can simply ignore all the cuts except the min cuts. This is simply because if you have a red cut, say failure probability p squared, and the larger blue cut, say with failure probability p cubed, since your p is goes to 0, and this p cubed is just an infinitesimal compared to p squared. So if you repeat this argument, you can remove the larger cuts and just keep the main cuts. Of course, the main cuts are still not independent, but they will not be too dependent. So we can, roughly speaking, they are somehow we can imagine they are independent. So your unreliability is simply just the number of main cuts times the failure probability of each main cut, which is p raised to the cut value. So in this extreme case, our problem is really just reduced to approximately counting the number of main cuts. And of course, this can be solved in many ways. We even know how to find all the main cuts in the almost linear time. But for the purpose of this talk, let's consider the following algorithm of sampling two respecting cuts on guide trees, which I will define in the next slide. So to define a guide tree, we start from this tree packing theorem. So if you have a main cut lambda, you can pack half of lambda as disjoint spanning trees. So they are like this. And like in this graph, you have like two edge disjoint spanning trees, the red tree and the green tree. And I'm saying I can do this for at least half of lambda. And now if you have a main cut, the main cut has lambda cut edges. And each span tree must use must cross the main cut, right? So must use at least one edge, but these lambda tree cut edges are distributed among the half of lambda disjoint trees. So on average, each tree will only use at most 2 cut edges. So in this case, we say the main cut 2 respects the same tree, which just means their intersection is at most 2. And now if we take log n random trees from the packing, we can guarantee that any main cut will to respect at least one guide tree with high probability. So now the problem is just reduced to counting the number of 2 respecting main cuts, which contains most of the main cuts. So given this, we can simply enumerate all the 2 respecting main cuts because there are just n squared of them. But since we aim for a linear algorithm, in self-enumeration, we can do sampling. So we can sample the 2 respecting cuts simply by randomly pick a guide tree and randomly pick 2 edges on the tree to define a cut. And we can repeat this n times because we can have linear time, and this can be supported by some efficient data structure. After that, we compute the ratio of main cuts among our samples and use that to estimate the ratio of main cuts among all the 2 respecting cuts. So this gives us some estimation of number of 2 respecting main cuts. Okay, one detail here is that these 2 respecting cuts might be repetitive because they are different trees, but this can be handled by inference. Okay, so our estimator is just the ratio in the sample times the number of 2 respecting cuts, and this will be the number of estimator of number of 2 respecting main cuts. So it is good, but it's good if your number of main cuts is larger than n, because you have like n main cuts over n squared space, and you pick say n log n samples, so you have good chance to hit the main cuts and get a good approximation of its ratio. But what if your number of main cuts is few, so you cannot hit them in n samples? In this case, what we want is to sample from a smaller guide tree. So this should be possible using some idea like this. So when your number of main cuts is less than n, there must be some components not separated by the main cuts. So assuming you can contract these components, this will not hurt any main cuts, but this will make your guide tree smaller. So now you can sample in a smaller subtree of size h with only h squared 2 respecting cuts, and now you are sampling n cuts, so you can still hit the main cuts. Okay. So this is for the simplified case, and we can reduce to the number of through selecting min cuts and just estimate this number by sampling through min cuts on gateries. In general, not only the min cuts matters, but maybe the smaller near min cuts also matters in your unreliability. But we still claim we can do something like what we did before. So we can first ignore all the large cuts. For large cuts, their failure probability will exponentially decay, so they are not important. And second, we can assume they are independent. So although these parts are dependent, their dependence is not too important in the probability. So if you assume this, then the unreliability can be approximated by the sum of failure probability of small cuts. Then for the small cuts, we can still capture them by our guide trees. So if you have a small cut of value alpha times lambda, this will be 2 alpha respecting in your guide tree. So this will, on average, only be defined by 2 alpha edges in the tree. So we can still repeat the same argument. That is, we do inverse sampling on the guide tree, but instead of picking 2 edges at random, we pick at most log n edges at random. And then this will define a k-respecting cut for some k less than log n. And now our estimator is its failure probability t raised to the cut value, and normalized by its sampling probability as inference sampling. So this will also give us a unbiased estimator, because now we just take the sum of all small cuts, and this sampling probability will cancel out. So we still get this sum. So the algorithm is like this. We pick a guide tree and pick some k to sample a k-respecting cut of k. Okay. But we still need to bound the relative variance for this estimator. And for that purpose, we need to bound the likelihood ratio. And this is defined by the ratio of true distribution over the sampling distribution. So true distribution is how this term contributes, the fraction of this term failure probability in your unreliability. So it's a p raised to c over UDP. And your sampling distribution is just 1 over your sampling space. For k respecting cut is n2 minus k. Because we are just randomly pick k edges and hope we can pick exactly that k respecting cut on tree. We want to bound this ratio to be less than n, so we can get a relative variance n, and we can get a good estimator in n samples. And if you use the guide tree as we described before, we can get something like n to 1.5. So this will lead to n to 1.5 odd-time algorithm. But in order to get a stronger bound of n, we really need some better guide tree. So this will, and this will be given by our ideal tracking. So next, let me describe, before describing ideal tracking, we start with this single observation. That, well, if you have any spanning tree and any k-way cut, the spanning tree must cross the k-way cut in at least k-1 edges, or you have to cross k-1 times. So this means if you have many disjoint spanning trees, each spanning tree must contribute k-1 cut edges. So the number of disjoint spanning trees is upper bounded by the cut value, which is the number of cut edges, divided by k-1, right, for any multiple cut. And let's call this the ratio of a multiple cut. And Unreliability theorem actually says the minimum ratio is tight. That is, the max number of fractional spanning trees we can pack is exactly the minimum ratio over all the multiple cuts. Okay. So for the purpose of finding a maximal tree packing, we can first find the minimum ratio multiple cut, and then let's say this is gamma, and then we we can pack gamma edges, and these gamma edges must be disjoint. Gamma trees must be disjoint on the cut edges, and this is possible. Okay, but for the ideal tree packing, we want a maximum fractional tree packing, and somehow we scale by gamma to get a fractional span tree, and we want to guarantee this tightness in the cut edges. Okay, so these cut edges will have load 1, and we scale it back to 1 over gamma. And we also want to ensure that this property is recursively true in these subgraphs separated by the multiple cut. So what we do is we find the multiple cut with minimum ratio and set these cut edges, the load to be 1 over gamma. And we recurse on the induced graph of each side. So let's look at some examples. So in this graph, we first find the mean ratio cut, and this happens to be the mean cut. So this ratio is 2, and we scale it back to 1/2. So now we have a load 1/2 in this edge, which just means you have 2, right? You should scale back, you have 2 span trees, and these span trees should be disjoint in this mean cut. And now we recurse on both sides of the mean cut. In the right, we have this mean ratio cut, and the ratio is 5 over 2. So we set load to be 2 over 5. In the left, we have ratio 6 over 2. So we set the load to be 2 over 6. So we have something like this, and this is a fractional span tree. In other words, it's in the span tree polytope and can be represented as a linear combination of span trees. Now we can define a guide tree by just randomly sampling from this linear combination. And the guarantee we have is the probability to pick each edge in your guide tree is exactly the load of this edge. Okay, so this is still some form of maximal span tree packing. So all the previous arguments for guide tree still work, but we have some extra structure which will help our analysis. And let me introduce some idea how this can help. So one typical case is when you have some induced subgraph. So this is just happen to be induced subgraph in our hierarchy, and it consists of many small cuts. So these small cuts will dominate your unreliability. There will be many of them, and their failure probability is large in total. But these are not mean cuts. So they might not to respect a normal tree packing, right? Their value might be, say, 2 lambda, 3 lambda. But thanks to the property of ideal tree packing, because we recursively ensure this constraint is tight for multiple cuts in the subgraph, so we can still expect these small cuts to be 2 respecting in our ideal tree packing. And this will allow us to sample from a smaller space for these important cuts. So instead of n squared n raised to a larger k, we now only need to sample from a smaller space of n squared. And we can also reduce this n in our sampling space by contracting some lower level components in the hierarchy of ideal tree packing. And this will lose some cuts, but because of the increasing monotone property of cut ratios, like smaller cuts are less likely to be contracted. So small cuts are likely to be preserved even if you contract some lower level of the hierarchy. So here, suppose you have some purple component, and that consists of many small cuts. But if you contract a lower level, say this blue component, you will not lose any purple cuts. And we hope that when we contract such a lower level component, we still preserve all the important cuts in our, that should be, like the smaller cuts are important. So if these 2 arguments, using these 2 arguments, we can get a smaller sampling space for important small cuts. So instead of n raised to k, we now have n prime raised to some k prime, and hopefully n prime is less than n and k prime is less than k. for important cuts in the unreliability. And so our algorithm will do this for different contraction levels, different subtrees, and try to sample the k-resident cuts in each contracting subtree. Right? So this ensures you really have n-prime risk k-prime sampling space in some level. So if everything works, then we can really get the likelihood ratio bound to be n using ideal track. So this is the ideal. Yeah, so in conclusion, this will be something similar to the original guide trees, but we need this help of stronger structure of hierarchical ideal tracking to give us some hint, if a cut is important, it can be sampled from a small space using our guide tree. Note here that the actual algorithm will be slightly worse because we only have an approximate ideal track, and we have to only take log n levels instead of too many levels. Okay, but this is more or less the complete algorithm. So our complete algorithm is some recursive algorithm of random contraction in unreliable case. But if we reach the more parallel case, or we reach the reliable case, then we can have a base case. And in the reliable case, we run this important sampling on guide trees, and the guide trees will be given by some ideal track, so they will have stronger property. And finally, let me come back to the random contraction and say some idea how we can improve the analysis. And this is again given by the ideal tree tracking, and actually given by this median ratio gamma. So recall that gamma is the median ratio over all multiple cuts of cut value over k minus 1. And previously we are using this lambda to define a parameter and do analysis. But now we can use this gamma, and since gamma is the tight bound for the maximum fractional trees you can pack, so this will be in some sense stronger for the analysis. And we can really achieve linear recursion using some parameter given by gamma and under some assumption given by unreliable case. And the main argument here is that we can get a stronger size decrease bound and a stronger relative variance bound. So the both arguments in our previous recursive analysis will be stronger, and we can really achieve a linear recursion. So some idea here is that for a size decrease bound, you want to use gamma to lower bound the density of any contracted graph. If your graphs are dense, intuitively it will contract faster, so will shrink to a smaller graph. And this can be done because gamma is the lower bound of all the ratios over multiple cuts. And notice that the multiple cut that separates every vertex into singleton is a multiple cut, and its ratio is just a density. If you define density in that way, so after any contraction, you can still consider multiple cut formed by separating all the components of a contraction. So this will also give you the density of any contracted graph. So you can always use gamma to lower bound that. So this will guarantee you have some fast size decrease. Yeah, and for the relative variance, some idea here is that, well, you have a mean ratio cut. So if your mean ratio cut is a multiple cut with many sites, then this will give you some many smaller cuts. So this will be stronger than parameter lambda, because lambda only give you one main cut. So you have more cuts, their randomness should somehow cancel out, and you have a stronger relative variance. Okay, so yeah, in conclusion, we have these two algorithms, and this ideal tracking can really have the analysis of both algorithms of recursive contraction and important sampling on guide trees. Yeah. So finally, let me conclude with some open problems. So first, this algorithm is for global connectivity. So we define the disconnection or connection to be discounting any nodes. But we can also consider other forms of connectivity. And most importantly, the ST connectivity. So we just want to estimate the probability to discount any a fixed pair of ST. Right. And for this problem, it's what we know by given by Feng and Guo here is, well, if you for the ST reliability problem, so the probability to connect, and on the DAG, so it's direct but just DAG. And then for that problem, we have FPTAS. And they also prove that for unreliability in DAG, it's hard. So it's harder than some problem which is conjectured to have no FPTAS. Okay, so this seems hard, but still, since we care about undirected graphs, right? So it's still open. Like we might get some FPTAS for ST like unreliability in undirected graphs. So this still like interesting. But this might be hard since we have some hardness result here for that. Yeah. Okay. Another interesting problem is can we get a deterministic FPTAS? So in general, for shocking hard problems, there are many randomized FPTAS. No, right? Some ideas should be similar. But for deterministic FPTAS, it's very little is known. So most related result here by Pito and Ricketts is that, well, they give some deterministic approximation of tilde polynomial, which is a much stronger object, so it includes reliability as a special case. And they can do this, but only for bounded degree graphs. So say constant degree. This is very, very weak compared to what we expect for general graphs. But it shows that this is not impossible, right? This is still interesting of a question. So, but the current algorithm framework is like heavily relying on the sampling and so on. So it's things far from that. But can we de-randomize such a unreliability? Yeah. Thank you for attention.